Hello, this is Mr. White, and this video is on solving differential equations using the separation of variables method. Here are the two exercises for today. All right, we start separation of variables by separating the x's and dx's onto one side and the y's and dy's onto the other. So we see that in this particular case we can do that by cross multiplying. So I get square root of x, or let's say x to the 1/2 dx, and I'll put that on the right side. And then on the left side we'll put the 3y times dy. And at this point, when you see the structure, the setup, and you see either the dx or the dy here, it reminds us of indefinite integrals. And the only thing missing is the indefinite integral symbol, which you are allowed, and in fact you should simply apply to both sides. So I repeat and I emphasize though that you don't do this until you have only y's and dy's on one side and x's and dx's on the other. All right, and then we proceed to anti-derive. I'm going to do the right side first. We'll get x to the 3/2, and then we need a 2/3 in front to balance it. And we'll put the plus c here. And then on the left side, we'll get y to the y squared. And then we'll have the 3, but over 2 to balance it out. And you may be inclined to do the plus c on this side and then recognize that this c doesn't have to be the same as this c. And in fact, it probably wouldn't be. So we would then call this c1 and then this c2. And if you were to do that, you might as well take this c2 and move it over to this side. Of course, what we were really doing was subtracting c2 from both sides. And now when you look at having one constant minus another, c1 minus c2, one arbitrary constant minus another, you might as well just call that a c unto itself. So there was my brief explanation as to why we typically don't bother putting a plus c over on the side with the y on it. So at this point we could go in a couple different directions. Most students, and I in fact, would probably be inclined to just go ahead and get y by itself. It doesn't look like it's going to be too hard in this case. So we would multiply the left side by 2/3 to cancel out that constant. And therefore, we'd multiply the right side by 2/3, which I'm going to go ahead and just distribute. So 2/3 times the first term plus 2/3 times the constant. And that's going to give us y squared equals 4/9 x to the 3/2. Now, as far as that constant goes, again, we've got an arbitrary constant here. Let's call it c1. And let's say that whatever that arbitrary constant is, when you multiply it by 2/3, let's say that equals some other arbitrary constant, c. So let's call that plus c. And it's pretty, I'll go ahead and mention that it's pretty typical throughout the separation of variables process to put a plus c and then redefine it and say, oh, I'm going to multiply that times 2/3 and that just becomes c. And so you'll get comfortable with that after a while if it seems a little bit strange right now. And of course, at this point, we would just square root both sides. Don't forget the plus or minus on the right side. So then we would just end up with y equals plus or minus square root 4/9 x to the 3/2 plus c. And we'll put a box around that. And a couple things worth pointing out at this point. Please avoid this classic mistake. Students every year want to do this. They see the 4/9 and they get excited because 4 and 9 are both perfect squares, and they want to believe that we can do this. 4/9 x to the 3/2 plus square root of c, and then they try to reduce this and make that plus or minus 2/3 x to the, that'd become 3/4. And then they say, okay, root c, well, that's just going to be a c. Any case, I hope you see the error here. When you have two terms being added underneath the radical, you are not allowed to split it into two radicals. Please don't be one of those who falls into that mistake. Another thing to point out, notice that the plus c is underneath the radical. It is not outside the radical where we're used to seeing it. When it is outside the radical, we're used to that plus c graphically representing a vertical translation. So for example, if we had a graph that looked like this, we're used to different values of c representing vertical translations of that graph. But that's not what we've got here. So what does the plus c underneath the radical do? How does that look graphically when you change the value of c? Well, we'll find out here in just a moment. But before we do that, one more thing I want to point out is that sometimes in the textbook or on test, you may see the answer expressed in a different way than this. An alternate way of handling this may be to take this equation written in blue here, and let's say we multiply that by 9, and we would get 9y squared equals 4x to the 3/2 plus 9c, which, one more time, if you think of that as some arbitrary constant c1, you can then just say, okay, 9 times c1, I'm just going to call that c. And at that point, you could subtract over the 4x to the 3/2. For reasons that I won't get into here, I'll just mention that this is another format of equation that you may commonly see. So don't be startled if you get this, but then the back of the book or a multiple choice answer has this instead. Okay, with all that being said, let's take this form of the equation and let's see what this looks like in Geogebra. I mean, again, really it would look the same in Geogebra, whichever form you use. But here's our graph, and if I go back to, let's see here, we notice the effect of the plus or minus in this form. We see how that results in a curve and its reflection across the x-axis. Okay, we see for the currently set value of c, where I have c set equal to 9, we see that that makes sense because if I plug x equals 0 and y equals 1 into this equation, we see that we would get c equals 9. And we see that this curve, this solution, does indeed go through the point 0, 1. So that makes sense. And let's see what this looks like for other values of c. We see that as c gets bigger, curve looks more like that. If I have c go back to being smaller, here's what it looks like when c equals 0. Looks almost like a sideways parabola, but it sure looks a little pointier there. And then, again, it's starting to look more like a parabola, although we could deduce that technically it's not a parabola. It just kind of looks like one. Okay, so kind of interesting to see the effect of the c, that you may have a single continuous curve for some c values, but for other c values it may break up into two different branches of a curve. Let me turn the trace on here. Okay, if I just leave a trace of the curve, we see something that should remind you a little bit of slope fields. If I've previewed slope fields for you already, try to make a connection between what you see on the screen here and slope fields. If we haven't seen slope fields yet, well, don't worry about it. But let's go back to a c value of, say, 4. And the last point I'm going to make about this exercise is that if I bring, notice that this curve now goes through the point 4, 2. And if I bring up that point and its tangent line, I want to now go back to our slide here with our calculations. And let's remind ourselves of the original differential equation, the original dy over dx. Let me provide a little bit of writing space here. And let's plug in that point that we decided to focus on, 4, 2. Let's plug in square root x value of 4 over y value of 2. And that's going to give us 2 over 6, which is 1/3. And we look at our picture, and we look at the tangent line, which also does appear to be going through that point, and we indeed see a slope, a rise of 1 over a run of 3. And that agrees with what we determined down here, that the slope is 1/3. So I want to remind you, again, what the original differential equation was telling us. It was telling us the slope, and from there we determined the equation, the solution, the curve. All right, so let's go on to the next exercise. With this exercise, the dy over dx is not written out explicitly, so we see it's expressed in a slightly different form. And we're also given an initial condition. Our solution curve must go through the point 150. So first things first, instead of writing y prime, for separation of variables, it really is preferable to write dy over dx. That's what y prime is. So we'll write dy over dx instead, and we'll get it onto one side of the equation by itself. So we'll have this 100x, we'll subtract over the xy. And now let's think about how we're going to separate the variables. How are we going to get this dx along with this x and this x on one side of the equation, and then this dy and this y on the other side? Well, students often make the mistake of just looking to addition, subtraction, multiplication, division right off the bat, and overlook factoring, which is going to be our ally here. Let's factor out the greatest common factor on the right-hand side, which looks to be an x, meaning that inside the parentheses we'll get 100 minus y. So now it would be appropriate to multiply the dx over to the right side of the equation. So now we've got x and dx together on one side. So let's divide this 100 minus y over to the left side. And we've accomplished our immediate objective of separating the variables. Again, x dx on one side, y dy on the other. We're going to integrate next. We're going to put the indefinite integral symbol. And what pattern do we see on the left-hand side of the equation? Well, sure looks like our u prime over u, doesn't it? If we say this is u, then u prime would be negative 1 dy. So we'll put a negative 1 on the outside to balance it out. And now I've got my u prime up top. So we proceed to antiderive, and we're going to get ln absolute value of u, 100 minus y, and then the negative 1 out in front means I'll put a negative sign there. If I antiderive the right side, we'll get x squared with a 1/2 in front, and we put the plus c only on the side with the x, as explained in the previous exercise. And we're certainly making progress here. We've just completed the calculus step. Now we've just got a little bit more algebra to go. We are going to try to get this function written explicitly. We are going to try to get that y by itself. Perhaps the obvious thing to do is to multiply both sides by negative 1 so that we can get rid of that negative sign. That gives us positive ln absolute value 100 minus y equals negative. Let's write this as x squared over 2. And we could put minus c, but subtracting one arbitrary constant is the same as adding its negative. So again, there's nothing wrong with putting minus c, but I'm just going to say, okay, let's call it plus c. So if I want to make a distinction here, I can say that in the previous line that was c1. In this line, I could call this c2. And again, the relationship might be like, let's say that if c1 equaled 5, well, then c2 would be its opposite, negative 5, for instance. All right, well, how are we going to get the y by itself? So it looks like the next layer to peel away on the left side is to tackle that ln. So the way we can essentially inverse that out is with its inverse function, the exponential function. Let's make that entire left side the exponent of e, in which case this entire right side needs to be an exponent of e. So here's a little bit of algebraic trickery. Pause if you need to, make sure you're getting all this. What we're going to argue is that this e and this ln inverse each other out, cancel each other out, so we'll end up with absolute value 100 minus y equals. Now, nothing cancels each other out on the right, but we can use our exponential properties, which say that when you have one term plus another term in the exponent, you could rewrite that as, in this case, e to the negative x squared over 2 times e to the c2. Once again, we're going to play some games with that constant, that arbitrary constant. If I have e, which is a constant, raised to this arbitrary constant, c2, let's just say that collectively, let's call that c. And I may later, if I play some more games of c, I may choose to call this c3 at a later point. But let's just call it c for now and see if that gets us to where we need to be. All right, we're getting close, so hang with me here. Where we're at, 100 minus y inside absolute values. And again, we're going to call that c, that e to the c2 here, calling that c, times e to the negative x squared over 2. Technically, there would have been nothing officially wrong with leaving it in this form or even leaving it in this form. There's technically nothing wrong with it, but every textbook, every AP exam is going to tend towards what I'm demonstrating here. Okay, and here's our last bit of trickery here. What are we going to do with those absolute value bars? Here's the way that I've found seems to make the most sense to students. If I just off on a sidebar say, hey, absolute value of n equals 5, solve that equation. Students can readily tell that, okay, n either equals 5 or it equals negative 5. So students acknowledge that this is the solution to that equation. So notice that in this type of application, that an absolute value bar over here is equivalent to a plus or minus over here. So let's apply that same reasoning to our equation. We'll remove the absolute value bars from the left-hand side, and we'll make it a plus or minus on the right-hand side. Make sense? I'm going to subtract the 100 from both sides. A couple ways you could go about this, but I'm going to subtract the 100 from both sides and then multiply both sides by negative 1. So notice that instead of plus or minus, I put minus plus. I'm not insisting that you do that, but I choose to. And instead of minus 100, it becomes plus 100. And in fact, one last point regarding that plus or minus sign. Let's think about this. Normally, we would need that, we'd leave that as part of our solution, whether you write it minus plus or plus minus. But in this case, since that minus plus is attached to a c, and it's already understood that c represents any constant, positive or negative, well, this minus plus is really kind of redundant and in fact useless. C already represents any positive or negative constant, so we don't need the plus or minus. It wouldn't be technically wrong to leave it in there, but you don't have to. And most textbooks or tests will not include it there. So let's get rid of it just according to convention and put a box around this. And we'll call that our general solution. We'll point out that in our textbook, for example, I've seen things like this. 100 minus ce to the negative x squared over 2. And on first glance, that looks like that's a different answer, y equals, of course. But one more time, since c represents any arbitrary constant, whether you have a positive c e to the negative x squared over 2 or a minus c e to the negative x squared over 2, it really doesn't matter for the general solution. If c turned out to be positive 5 up here, well, that's the same as c being negative 5 down here. Make sense? All right, let's see what this general solution looks like for different c values in Geogebra. Okay, here's our solution when c equals positive 200. As I start changing the c value, we see that that mountain shrinks and shrinks and shrinks and turns into a valley. So here's c equals negative 200. If I decide to turn on the trace, I see a whole bunch of those representations of different c values all at once. Kind of a cool pattern. All right, so now that we have a sense of what this general solution looks like, all these different c values, let's recall that we had an initial condition that we were supposed to observe. So if I go all the way back to top, I see that we had this initial condition, y equals 50 when x equals 1. So where is that going to be? Right there. Okay, and so we want the solution that is somewhere around there. Visually, I can see now that with the help of Geogebra that I want a c-value of about -80, but I can't tell if it's going exactly through that point, and we really need to do it algebraically anyway. So let's go back to here. And I'm going to plug those initial conditions values. I'm going to plug x equals 1 and y equals 50. I'm going to use my original solution. So I'm going to plug in x equals 1 in this equation, and then y equals 50 right here. Okay, and that's going to give us 50 equals c e to the -1 squared over 2, or just -1 over 2, plus 100. And at this point, I'll subtract 100 from both sides. That'll give me -50 over here. And then I'll divide by the e to the -1/2. And that will give me c all by itself. Okay, let's put the c equals over on this side. And then I'll type into the calculator. And I'll find that that's approximately -82.436. which is not too far off from what we predicted it would be in Geogebra. So our particular solution would therefore be y equals c, which we said is -50 over e to the -1/2 times e to the -x squared over 2 plus 100. Some variations that you're likely to see. First of all, in some contexts, we might just go ahead and plug in the decimal approximation there as a coefficient. That depends on the situation. Now, what we're more likely to see is we're unlikely to see a negative exponent in a denominator. Let's remind ourselves that that's really the same as -50 divided by e to the -1/2. That's the same as times e to the +1/2. And then times e -x squared over 2 plus 100. And keeping in mind exponential properties, you've got the same base here, and might as well add their exponents. Okay, I know that was a bit much. I hope that didn't overwhelm. One more time. This has been our particular solution, which you see in its various forms. If I go back to Geogebra, I see that when c equaled -80, that again, it was just close. I've turned on the coordinates here. But when I set c equal to the value we just solved for, approximately -82.436, we see that it does now go through 150 more precisely. And furthermore, if I show its tangent line, I trust you're getting the idea now about what the differential equation tells us about this curve and how it tells us the slope of the tangent line. So if you were to plug in the x and y values at any point along the curve into the original differential equation, you would get a true statement.